Have a great day, students. Today we are going to see about the Unit 3, the topic of Unit 3. It's light semiconductor interaction. So, what will happen when light is passed on to a semiconductor material? So, first let us have a recall about the semiconducting material. You know, semiconducting material, it has valence of that is equal to valence C equal to 4. It's normally in the case of germanium and silica, which are the naturally occurring materials. So we have seen this n number of times. Now, what about the energy band diagram for a semiconductor? So if it is a pure form of semiconductor, then you have the energy bands like this. The bottom one is mentioned for EV, so it is starting from the lower energy level. In the previous unit we have studied that minus infinity to EV, and when it start to move from the valence band, actually what is happening in the atom, so you know that the center you have the nucleus, and the electrons are revolving around the nucleus in the form of orbit. So the outermost orbit consists of the valence electron. So when some energy is given, it comes out. So it becomes free. The electron becomes free. So this is what happening normally. So that is written or that is represented or illustrated in the form of energy band diagram. So the electron which is revolving around the nucleus, which is nearer to the nucleus, so that is they have the lower energy. When it is when you move from the center to outwards, so the other orbit, if you have another one orbit here, then it has the electron moving around. They have a high kinetic energy because here it is affected by this um, nucleus. Okay, and the outermost orbit, the electrons have more energetic. So this thing is drawn here in the form of energy band diagram. So minus infinity to EV, and when it start to conduct, it move to the conduction band. Okay, so you have the electrons here first. So when they move to the conduction band, it forms a hole here, right? So these things also we got discussed, right? So normally in the first two units we have discussed that the heat energy is applied. When heat energy is applied, the electron will move. When the temperature is more, the electron move from the valence band to the conduction band. So that we have studied. Now what happens when light is passed? So when light is passed onto a semiconducting material, so that we can see in detail. Okay, so here I am going to give an outline about the different topics we are going to see under the title of light semiconductor interaction. So in this unit we are going to see these things. The first one is optical transitions in bulk semiconductors. Okay, how the transition takes place when you pass the light, how the transition takes place from one energy level to another energy level in the bulk semiconductors. So it includes the absorption, spontaneous emission, and stimulated emission. So as like the laser, the same kind of thing we are going to see here. And In addition to that, joint density of states, then density of states for photons, transition rates, so it includes Fermi's golden rule, then optical loss and gain, photovoltaic effect, exciton, and finally a Drude model. So these are the things we are going to study in detail. Okay. So here, joint density of states. Normally, we have discussed about the density of states in the case of metals and semiconductors like intrinsic semiconductor, then N-type semiconductor, P-type semiconductor, etc. So here this joint density of states, this involves when the photons interact with it, so it forms a hole as well as an electron, which means the electron in the lower energy absorbs the photon and move towards the higher energy state by leaving a hole in the lower energy state. So that is the case. So joint density of states involves the both electron and hole involved. Okay, that you will see in detail while discussing that particular topic. Now, let us see the first one. Okay, so optical transitions in bulk semiconductors. So first one is absorption. First one is absorption, which is just similar to that of the laser, but there we have discussed about the atomic transition. Here it is electronic transition because electron movement we are discussing here from one energy level to another energy level. Atomic transitions in the case of laser. Okay, now here you can see what is happening. A photon of energy h nu, a photon of energy h nu is applied so that the electron in the semiconductor absorb the photon and move towards a higher energy state. Okay, so from here to here, that is E1 to E2. So that is what mentioned in the description too. So the absorption of the photon causes atom or molecule to transition from a lower state to higher state. That is nothing but the transition. So here it is transited to the excited state. So as we have discussed, it involves the absorption, then spontaneous emission, and stimulated emission. So in this you can see the transition. What are the transition takes place? Absorption, spontaneous emission, and stimulated emission. So second process is spontaneous emission. At first what happened? Lot of electrons from the lower energy level move towards the higher energy state or the excited energy state, so that more number of electrons occupy the excited state and it leaves more number of holes in the lower energy state, that is below the valence band. Now here you see what is happening in the spontaneous emission. The atom in the excited state first, before the emission process, the atom is in the excited state. So during the emission, it comes down automatically. So spontaneous means automatically it will comes down by emitting a photon. Okay, so the process is clearly similar to that of the laser. To the laser. Now, in the first process, I want to say some more concept. In the first process, there is an absorption case. Okay, so here they have mentioned only one energy level E1, E2. So actually, normally what is happening means there, if the energy of the photon is more, by the absorption of energy, so it consists of electrons in different energy levels. In the bottom energy level also you have electrons. Okay, so you have electrons. So when it absorbs energy, so if the energy is more, it will get more kinetic energy and move towards the excited state. And so some of the electrons, what happen means, it will move towards a higher energy state of the conduction band. Okay, not in the starting point of the excited state or the conduction band energy. It will move into the conduction band energy. And some other electrons can even occupy even higher state in the conduction band energy. So these possibilities are there during the absorption. Okay, right. And we have the follow-up of spontaneous emission too. Okay, so statistical process, it is a random phase. Randomly this takes place. Okay, so here actually here this is not explaining about the atom. Okay, here it is about the electron. It is about the electron. Okay, so you must mention as electron. Maybe there is this is the wrong diagram chosen, but this is mentioning the electron. Okay, right. So and more is there. Yeah, so stimulated emission. Now you know about the stimulated emission. At first there are more number of electrons in the higher energy state. Now you are passing the light into it, so the light interact with the electron in the higher energy state. That means it absorbs the applied energy. Okay, so already it has the energy of E is equal to h nu because it absorbs the energy and moved to the higher energy state. Now when again it interacted with the photon, it absorbed that and it will comes down. It will comes down by emitting two photons. Two photons. So this is, if it is said to be E is equal to h nu, and this is also E is equal to h nu. So the total energy is 2h nu. Okay. So here the stimulation takes place. Stimulation takes place, not done automatically. This is initiating the emission. Okay, so this is the difference between spontaneous and stimulated emission. So here there is no random propagation. So this there's the same direction of propagation. So this is about the stimulated emission. Now putting all together here, first the absorption is taking place, and so this is explained with the help of just two state. Normally we have different energy states in the high excited state as well as in the lower energy level. That means that valence band as well as the conduction band. So first absorption takes place, then spontaneous emission takes place, and again the stimulated emission also taking place there. So that's all about this. So I can provide the notes corresponding to this. So this is a big question. Okay, so you can go through that. Now Next one is joint density of states. So I said already joint density of states because it involves the um, both the holes and the electrons. Okay, so the frequency dependence of epsilon I of omega results mainly from the summation over both initial and final states satisfying energy and momentum conservation. So here there is a frequency dependence or dispersion of this epsilon I, which means the energy transfer. So here that is given by satisfying the initial and initial and final states energy. So here you can see summation of k delta of EC of k minus EV of k. So here you can see EC is the valence band energy and V is the EC is the conduction band energy and V is the valence band energy. So minus h cross omega. So from this you can get the frequency dependence of this epsilon I, which gives the energy difference. So the summation over k can be converted into integration over the interband energy difference. So within how much energy level the energy difference is there, so that we can so ECV is given by EC of k minus EV into k by defining the joint density of states. So the density of joint density of states is given by dj of ECV. So as I said, the difference between conduction band as well as valence band. So that is equal to 1 by 4 pi cube integral of d sk divided by delta k into ECV. Okay. So for these expressions, we can derive these things during while we study this giant density of states. We just understand. So here we are taking both the conduction band energy as well as valence band energy, since the energy absorption involves the electron as well as holes. So Fermi's golden rule. So here, in order to determine the probability or amplitude of the absorption, how the light, that is the photon, is absorbed, the amplitude of absorption, okay, how much energy can be absorbed. So that must be find by the overlap of initial and final wave functions. Okay, so this is some mathematical concepts here. Initial state and the final state. So the wave starting, final state, initial state and final state of a single particle. So that means a movement of electron from initial state to final state. So that is given by this Fermi's golden rule. So this is here. The probability of absorption or emission will depend on overlap, the overlap and the energy difference of initial and the final state and the density of states. Okay, so it always depends upon the initial and the final state, the energy difference between the initial and final states. So these things are discussed based on the movement of electron from lower energy state to higher energy state. Okay, so just keep in mind what we have studied in the first 2 or 3 slides. Okay, so that's it. Then, so this gives the quantum structure case. So choice of wave function for initial and final states. So two different kinds of possibilities are possible in the quantum structure. So the transition is between the valence and conduction bands. One is happening between the valence band and conduction band, and another one kind of transition that may be possible within the uh, conduction band itself. That is the lowest energy level in the conduction band to the highest energy level in the high conduction band. So that is also possible. So that is called as inter subband transitions. Inter subband transitions. That may also be possible in some cases. So that is given here. Okay, so this is about the quantum structure case. And the photovoltaic effect. So photovoltaic effect is somehow closely related to the photoelectric effect. Here what is happening from the name itself you can say when photons are incident on a material it will produce the potential difference that is in the form of voltage. So this is used in the application of solar cells. Um, so there is nothing but the photovoltaic effect. So here during the absorption there is some interaction will take place between the electron and the hole, and that is said to be the excitonic effect, that is the electron hole interaction from the lower energy level to higher energy level, that is the valence band energy to conduction band energy. Okay, so the remaining things we can see in the next yes. So thanks for listening students. Let me connect with you in another one video. Thank you.